So let's see. Last week we went through last week's actually we went through different things, different topics. We did units, we did the Schrodinger equation. We understood why the Schrodinger equation is important, because it provides both the eigenvalues, right, and the wave functions, and these wave functions add more knowledge to our picture, because it can determine different properties of assuming that we know the wave functions, right, and so on and so forth here, and more properties, any properties, everything, the system, anything which is given by the quantum world. The only limitation is the uncertainty principle, right? Which tells us that you can never know two properties at the same time if they don't commute. Some properties, these guys don't commute, and this one is equal to IH bar. So this was a Heisenberg's uncertainty principle, and now our purpose will be to determine E and psi, the wave function or the eigenfunctions, for a given problem, right? So we solved the other day the problem with when we have the rotational energy. The Hamiltonian was equal to T plus V, but in a rigid rotor, the distances here are always the same. So V is equal to 0. So this was given by the kinetic energy in a rotational motion, which was given to Lx squared plus Ly squared, or in nuclear physics, we call this Jx squared plus Jy squared. And as we know, this was given by J, you can make the substitution of J squared minus J Z squared, right? And in such a way, we deduce the eigenvalues of the rigid rotor. And Luazzi and you guys managed to get very nicely Hy squared over 2 times the moment of inertia. And we say was J plus 1 minus K squared.
Prof.
But tell me.
We can't see. Maybe you.
Oh, sorry, guys. Sorry. Again, I always make the same mistake. I'm making a freshman mistake not to share the screen. What is the screen now? Sorry about that. So I didn't share the screen here. Sorry. Thank you for letting me know. Just let me know, because lately, I don't know, I'm making this mistake. So basically, I was telling you that that we have been solving the Schrodinger equation already, and we solve it for the case of the rigid rotor, where in the rigid rotor we have the situation that the potential energy is equal to 0, because this distance doesn't change, right? So as this is the case, this is 0, and only we have the kinetic energy, which is Lx squared plus Ly squared, or for the total angular momentum, Jx squared plus Jy squared. So we interpret that the Niels Bohr interpretation of the hydrogen atom was beautiful, musicality for the human thought, but it wasn't enough, and we needed the wave functions, because the wave function allows us to determine more things, and we did X, P, all these operators. We have the also transition probabilities we discussed that we can also determine from the wave function. The wave function provides all the information that is available in the quantum world, and is only limited by the uncertainty principle, right? And this uncertainty principle tells us that two properties, the X and P, cannot be determined simultaneously, and there's always an uncertainty intrinsic to this property, which is the uncertainty principle. So from here, from the Hamiltonian, and assuming the potential energy was 0, we deduce what is the classical energy, and we quantize it, and we deduce finally the energy of the rotor. The energy of the rotor was given by this, but as we say that the rotor is rotating with respect to the symmetry axis here, and this K is the projection of J onto the symmetry axis. There's no projection because it's just perpendicular to the symmetry axis. So for the ground state band, the K quantum number is assumed to be 0. It's not 0 many times, most of the times, because as soon as the rigid rotor start doing something else and move from J here to somewhere J here, then obviously you're going to have a projection here, and K will be different to 0, right? But anyway, for the ground state band, we assume it is equal to 0, and we deduce the different levels. We have the 0 plus, the 2 plus, the 4 plus, and the 6 plus up there, and they follow a very particular pattern of, if this is 100, we say that this is 333, and this was like 698 or something, I don't remember now. And the gamma rays, which are the difference between these two, guys. So the difference, there's no EJ is the energy of the state, and E gamma is the transition. So EJ plus 1 minus EJ, right? So E gamma is this transition here, and is not to be confused with the energy of the state, right? Which is what this is characterizing. So now we move to the going to close this one, and we are going to open a new one, because now we know what the nucleus is doing, and we deduce also the energy spectrum, which as we discussed the other day, it looked like we have here counts, and here we have energy here, energy in whatever units, in kV generally, but it can be MeV, counts here, and then we deduce that we have these peaks, right, in the spectrum with some background, and these peaks, they actually were quite equidistant in energy here, and this was the property of having this formula. So we know if we look at the spectrum, 2 times the moment of inertia, J plus 1, we know how a spectrum would look like if the nucleus is rotating, right? Today, we're going to wonder, let me just put this right, if the nucleus is rotating as a whole with respect to a symmetry axis Z, right? And this is angular momentum J. So we know what it's going to do. As we say, we know the level scheme 0, 2, 4, 6, and this is what we see. And it goes on to 20, 30, 40. All these are units of h bar, right? So when we say 4, it's actually 4 h bar, right? When we say 2, it's actually 2 h bar. So the angular momentum, as we know, is quantized in terms of n times h bar, right? And the parity also is a very important thing, is equal to -1 to the L, right? So now we move, and we're going to do something else. We know this. We are going to move to see what a nucleus will do if it will vibrate. So let's start from scratch. Let's try to identify. Let's see what happens. What is kind of a spectrum, what kind of excitations we will see if a nucleus vibrates, right? So in this case, although we're not following the if we open the, I'm going to send you this after the lecture. But if we open our nuclear nodes, which have been changing quite a lot lately. So we're moving here to chapter 5. And we're moving here to the harmonic oscillator potential, 5.3. So we don't know anything about the shell model yet, but we're going to explore the harmonic oscillator. So this is in the new edition I'm sending you is the page 48. And we're going to deduce the energies of the harmonic oscillator potential. So things are there, more or less, explained, but you need to explain things. They're not in super detail. So we need to ourselves to do some calculations. So we know in our particular case, we're going to have to solve the Schrodinger equation again. But in this particular case, the Hamiltonian will have a kinetic energy and a potential energy. As it is a very good choice, it's a very good choice to select a potential with these properties. This is the potential, which is V equal 1/2 of kx squared. And here we have x, and here we have the nuclear potential of Vx, right? And our goal is to determine all these levels which are bound for a nucleus when the nucleus is doing something, is actually oscillating or whatever it is doing. We're going to study, in this particular case, nuclear vibrations. So how does a nucleus which is vibrating look like, right? This is the question. This is the question that we want to answer. So then for that, we are going to solve again the Schrodinger equation, and the Hamiltonian will be equal to P squared over 2m, that's the kinetic energy, plus 1/2 of kx squared. We are treating this in the first case as one-dimensional problem, although we know that there's no such thing as one-dimensional problem. We have to eventually move to the 3D, which is the real case. We live in a 3D world, and this is what we have to see. Right away, we can see there's an issue here because this guy goes to infinity, and infinities are not good partners in mathematics, right? All these infinities, they lead to mathematical issues, but we're interested here in these guys, which are the bound states, right? The bound states for this nucleus which is vibrating. So now we remember that we have let's keep exploring the Hamiltonian. The Hamiltonian will be equal to P squared over 2 times m plus 1/2 of k. K, we're going to substitute k by k, the wave number, right? So m omega squared, x squared. And now we are going to make a little bit, we're going to multiply here h bar omega and multiply and divide by h bar omega. So we're going to have, let's say, 1/2 of m omega, and omega, they're going to, 1 omega is going to be dividing here, so it's going to cancel with this omega, and we're going to have an h bar here. So basically, I'm just multiplying this term by h omega and dividing by h omega. That's why h bar is here, because there was no h bar here. X squared. All these guys, they have a head here because they are operators, right? At some point, I will remove those operators, but all of them, remove those heads, but they are all operators. Plus, and here we have 1 over 2m h bar omega p squared. So this is a Hamiltonian that we need to solve. And now we're going to make a little entry here. This is the Hamiltonian, which seems easy, but it is actually quite complicated to solve. So we have different, I'm going to show you a couple of methods solutions of the Schrodinger equation with the harmonic oscillator potential, we can use cylindrical coordinates. And in such a particular case, things become quite tedious. It's okay. It's a nice method. We use the Nikiforov-Uvarov, method to solve this problem, and we have to solve these big differential equations, right? They are using cylindrical coordinates, but they have to solve the problem by series, by power series. For instance, let me see if there's some. I have something here. Let me see. No. Probably here. Let's see the quantum harmonic oscillator, and we can solve it by power series method. And this is the similar way to how we solve the hydrogen atom. When you have more than one proton and more than one nucleon is very important. But as you can see, the situation becomes mathematically quite complicated. You see, so we have to solve this by series. We reach this equation, the eigenvalues and the eigenfunctions, but we're going to do this in a different way because we don't know how to solve differential equations by series in the first place. We can learn, but we're going to use something else which makes the problem simpler. And this something else is going to be called, I think CP mentioned this in his lectures. And you're going to correct me if this is not right. Did CP mention about second quantization? Huh? ¿Lo hace? Did CP mention about second quantization? Can you hear me?
We can hear you, sir. I'm not sure.
Okay, let's see. Let's see now. You're going to learn a little bit more. So I just wrote down the Hamiltonian in such a way because then I can remember easily. We're going to introduce here what is the annihilation operator. It's going to be equal to m omega 2 h bar. And then it's going to be square root of x plus I, and then here 1 over 2m h bar omega 1/2 of p. And this is going to be called the annihilation operator. Or destruction operator, or lowering operator. And similarly, we are going to define the A dagger. This symbol means define, which is going to be equal to m frequency 2 times h bar 1/2. So you see, it's the same thing as we have here and the same thing as we have here. X, this is square root. We put the x down a little bit down so it doesn't look like it's multiplying. X here, a square plus, actually minus, sorry, minus the same thing, I 1 2m h bar omega square root of operator p square. Right. So this is basically the second quantization, and this is called the creation or rising operator, right? Is rising operator. Okay. So now we are going to start playing with this operator. And we're going to make to convert this X and P into A and A dagger. This is symbol is a dagger there. So, and this is an X. So for that, what we're going to do is to add and subtract these two equations in a way that we can get what is. So this doesn't have a square here. In a way that we can deduce what is X and P, right? So to do so, is a good exercise that we do it ourselves, but there's a lot of calculations to do here, so I will do it myself. So if we, actually, I should have, let's go to a new page. You can always watch the video and follow the video with the questions, but you write the questions yourself in a piece of paper. Let me see again. Plus, I got to write small here, small size, so I can do all the calculations that we need to do. So we have a Hamiltonian. As I say, I cannot memorize things, so I have to start from the beginning. T plus V equal P squared 2M plus 1/2 of K, which is M omega squared, X squared. And this is going to be equal to H bar omega. And I'm going to multiply and divide by H bar omega. So I get the M omega divided by 2H bar X squared plus 1/2M H bar omega P, right? And from here, I'm going to define A, which is equal to M omega. Let me put this more size here. M omega 2H bar 1/2 of X plus 1/2M H bar omega. An I here. 1/2 of P and a dagger, which is going to be equal to the same thing, M omega 2H bar 1/2 of X minus I 1/2M H bar omega 1/2 of P. And now let's go here and let's add these two guys together, right? And then we have that X, or let's say A plus A dagger will be equal to 2 times this thing here, right? M omega 2H bar 1/2 of X. So X equals, so this goes up, A plus A dagger. Remember, these are all operators, even if sometimes I forget. Divided by these 2 is the square root of 2. This will be a square root of 2 here. H bar M omega 1/2, right? That will be X. And similarly with P, we do the same. We just, there was adding these two guys, these cancel each other, right? Now we subtract these two equations, equation 1 and 2. So here what we did was to do 1 plus 2, right? And now here we do 1 minus 2. And we get rid of these terms here. So we have that A minus A dagger equal 2I 1/2M H bar omega 1/2 P, right? So in a way that P is equal to A minus A dagger in this case. Divide also, this goes up, this goes down, square root of 2 I comes dividing here on the other side and multiplying these fellows to h bar omega 1/2. Okay, so things look so far a little bit complicated, but they are actually not. We're going to get things much easier from having this substitution here, and then we're going to see it right now. So now we go back to our Hamiltonian, right? And we're going to substitute here x squared, which is here, and p, which is here, right? This is actually p squared, right? So now we go and say, okay, the Hamiltonian is equal to h bar omega, and we're going to put this thing here, m omega to h bar, and now let's put x squared, this guy square. So it's going to be a plus a dagger square. I'm going to not to put the hats, but remember that these are operators, right? And the operators have particular properties that we're going to investigate further in a little bit. So a square root of x, this square root becomes a 2, right? And these guys becomes h bar m omega. Now, as you can see, we are simplifying things very much, because here we go. These guys all cancel each other, and this guy becomes a 4. And then we say plus 1 to m h bar omega. I'm just converting this here, right? And p squared, which is a minus a dagger square. I squared is minus 1, as you know. I squared is equal to -1. So this negative will become this positive will become a negative. Here, this is a negative sign. And the square root of 2 will become 2. And 2m h bar omega square will just become 2m h bar omega. Right? Actually, no, this 2 actually is out of here, because we make this square root of 2. So when we did this 2, and this 2 became a square root of 2. These two 2's remain just one square root of 2, right? So we have basically a square root of 2 divided by 2, which is, you multiply a square root of 2 in both sides, right? You will get that this is 2. And you have 1 over square root of 2, which is what we have right here. So that square root of 2 implies that this is not there. This 2 is not there, but the square root of 2 has become a 2. And these guys, again, m, h bar, and omega, cancel with these fellows. And we have a remaining Hamiltonian, which is equal to 1/4 of, let's put the 4th outside. Let's put the 4th outside here. Let's put 4 here. And then let's see a plus a dagger square minus a minus 2, and 2 is 4. It has gone out here. A minus a dagger square, right? Are you following, guys? Are you following so far or not?
Yeah.
Okay. So now here we are going to use a property. Now the operators, I would say, you have numbers x plus y squared, right? This will be x squared plus y squared plus 2 times xy. But this is not the case for operators. When you have operators like a plus a dagger square plus a dagger square, then this is a dagger square plus a square plus a dagger square plus a dagger plus a dagger a, right? This is not the same as 2a dagger. Is that clear? So when you have operators, it's not the same there's no commutative rule here. A daga is different to A daga A, right? For that to see, you can have you can put a ruler, and you can say, okay, let's take the ruler, and we have a 3D ruler here. Let's use a different color, and we move it first to the right. It will look like this. We'll turn it to the right, and let's use a different color here, and let's bring it up another degree, another 90 degrees here, right? So this guy will become, final ruler will be placed up there, right? However, if we do the opposite, you have moved A here and then there, we have rotated to the right and then to the right vertically. But if we do the opposite, right? If we have this ruler or whatever you want to have, it has a. So if that we are not in the class, so I'm gonna show you with the actual ruler. But if we actually, instead of moving one to the right and 90 degrees vertically, right? We do the 90 degrees vertically first. We do this one first, then the ruler will look like this, right? And if we rotate it 90 degrees, the ruler will look, now we look 90 degrees, the ruler will look different than what we have here before, right? Let me see if you can see that. So we're moving this ruler. Let's see, we have I mean, we can have something. Let me see if I'm going to see here. I'm going to stop sharing because I want to show you with the cell phone, right? With the cell phone, we're going to see. So we have a cell phone like this, right? And we're going to rotate it 90 degrees first this way and 90 degrees this way. So it looks like this, right? So let's go back now to the position. So we did 90 degrees this way and 90 degrees this way. Now let's see. If we do first 90 degrees this way and 90 degrees this way, does it look different than if we do the opposite, right? Let me see again. We do this 90 degrees this way and 90 degrees this way. Or we do 90 degrees to the vertical and then to the X, right? Let me see. You see the difference? The outcome is different, right? We have this face here, and the other case, we have the other face. Let me see again. So 90 degrees this way, 90 degrees away. If the screen is pointing up, 90 plus 90. But if we do this 90 plus 90, now we have a different. We have the same, no? 90 is different, right? Let me see, 90 plus 90 or 90. Let me see. We rotate it like this, and 90 is the same now. So let me see. What we're doing something wrong. It must be different. So this move like this. Okay, yes. They move like this. Look, 90 degrees to the right, and then we move vertically like this. Right? This is the situation. So this is what we do. We do moving 90 degrees and then 90 degrees. Right? So this is the situation versus if we do 90 degrees and 90 degrees. Right? This is actually what we're doing right. So in the first case, we rotate to the right with respect to the plane, right? And we move vertically, and we get the cell phone is like in this orientation, right? So we can do it 90 degrees first on the Y, and then we get this, right? So let me see again, this plus this, different to this plus this. So we are doing the same thing, but in different order. Do you see in Fundo now? So
yeah, I see.
Rotating right, and vertically. we do the vertically first and then right. You see, it's different that whether we rotate first on the plane and then do the y rotation, or we do the y rotation and we get this, right? So we are doing the same thing in inverted orders, and it looks different. So this is the problem with operators, or the thing with operators, that they cannot be used in the same way as numbers, right? As we just, I think in this case, let me see if we can do it again. So we just, I know it was a little bit confusing, that one, but okay. So we move it right. Let me see, they move it right. It was like this, we move it right, and then vertically. So vertically, the green color, vertically, we will have the cell phone pointing like this, right? On the side. So if we do the opposite, let me see again, we have this 90 degrees, and we move it vertically. So it will be like this. Now it will be like this. And here we have the axis. We are moving on Y. We're moving here onto the X. Actually, sorry, the Z here, the Y. And then finally, if we rotate, this thing will look, the final outcome will look entirely different, right? This will be the final outcome. And this will be the final outcome if we do it the other way around. Is that clear now? Huh? I think with the cell phone, you can easily identify, we first rotate to the right and then vertically. So it's different than doing the other way around. I hope you are convinced on that. If so, the first step matters here. So then, if that is the case, the mathematics of operators is a little bit different. Two numbers, and in that situation, this will be h bar omega for a square plus a dagger square plus a dagger plus a dagger a, right? Minus a square minus a dagger square minus a dagger square minus actually which becomes plus a dagger minus, if you have numbers, there will be x minus y square will be x square plus y square minus 2xy. In this case, in operators, a minus a dagger will be equal to a square plus a dagger square minus a dagger minus a dagger a, right? So this minus and minus get positive here, and here we have a plus a. So this becomes actually equal, the Hamiltonian becomes equal to h bar square, sorry, h bar omega. I was thinking about the 2 here. These guys cancel with each other, right? This guy cancel with each other. And then we have 2 times a, which has been already converted here, a dagger, 2 times a plus a dagger a. So 2 times a dagger, we have removed this 4 and we have converted into 2 because it was 2 times here and 2 times here, right? So this is the Hamiltonian. The Hamiltonian has been quite dramatically changed to something much simpler than whatever we have originally right here. And this is the beauty of second quantization, right? So this is the beauty of second quantization, because now we have another property that this is a concept that you're going to investigate, and we have a property which tell us that a dagger is equal to 1, and this is for you to prove. This is for the bin, right? This is for the bin full of paper, and I want you to calculate this knowing that xp is equal to I h bar. So you're going to deduce this a dagger equal to 1, because a dagger, and this is a key to solve this problem, is equal to a dagger minus a dagger a. So this thing becomes h bar omega over 2, and we can substitute. We want to substitute for the following reason, because we know that a dagger a is equal to n. N, I'm going to mention in a little bit, is equal to 2m plus L. So we know what is a dagger a, but we don't know what is a dagger. So that's the whole point. So a dagger, we're going to substitute by this is equal to 1, as I say, right? So let's go down a little bit so we don't get confused. So a dagger a is equal to m, but we don't know what is a dagger, which is equal to 1 plus a dagger a. This comes from the commutator here. So we substitute this over there, and we have h bar omega 2 times a dagger a plus 1, right? This is what we have just done here. And we can carry on now, and this is what we know, that a dagger a is equal to n, and n is equal to 2 times m plus L. We know this from quantum mechanics. So basically, we solve the Schrodinger equation, and then let's put this thing there. 2 times n plus 1, which once we solve the Schrodinger equation, the eigenvalues will be given in terms of NL, which will be equal to h bar omega 2 actually, this 2m plus L plus 1 here. Or plus 1, let's remove this, let's put this 1/2 here, h bar omega, and that's it. The energy of the harmonic oscillator is going to be equal h bar omega. Excuse me. Normally we call this frequency omega naught, but doesn't matter. 2m plus L plus 1/2. And this will be the energy of the 1D, the one-dimensional harmonic oscillator. These are the eigenvalues that we have deduced. This is something else that I want you to deduce, that a dagger a on a wave function is going to be equal to n L. So these are the mathematics that we need to deduce ourselves. This one, and also this one. These are the problems that I want you to calculate, so we know entirely what to do here. So then the Hamiltonian in a 3D, it will be, as we say, this is the 1D harmonic oscillator, but in 3D will be I equal 1 to 3, and then let's look at the Hamiltonian here. Is here, up here. Let me see, let me say, move this to 1/2 here. Remove these fellows, I know. So that will be a h bar omega, a I plus 1/2, right? plus the 1/2 here. You need just to follow the calculations later on and do them yourself, right? But which will convert to the energies of the harmonic oscillator in 3D, which will be h bar omega 2m plus L plus 3/2. So that's the only thing that will change. And this will be the energy of the harmonic oscillator in a 3D, right? The energy, the eigenvalues of the harmonic oscillator in 3D. So we have deduced this from using the second quantization, as you can see from here, which is quite complicated. Either we go the difficult route of doing by power series, which is very complicated, or more complicated than what we have done, or we simplify the problem by using second quantization and the A and A dagger operators, the annihilation and creation operators. We simplify the problem to a Hamiltonian, which is equal to h bar omega A dagger A plus 1/2. This is quite simple, right? To solve if, when we know that A dagger A is equal to the number, total quantum number n. And the total quantum number n is equal to 2m plus L. So basically, now we're going to have states which are defined in terms of these quantum numbers, n and L. N will be the major quantum number, harmonic oscillator quantum number, and L will be the angular momentum quantum number, and it will be S, P, D, F, G, 0, 1, 2, 3, 4, and so on and so forth, right? So now we are in a position, once we have solved the quantum problem, we are in a position to answer our question about how vibrations look like. But before that, I want some questions here. Because I know that this is what we have to do. We have to solve this ourselves. We have to go through these equations. We have to solve these operators. We have to remember that the operators, they have quantum operators. They have a different properties, right? They are not 2 times A dagger, but they are A dagger plus A dagger A. So, guys, questions here. Sialoa? Manfred, anything? I'll keep sharing the screen because then we can see what we're doing. So this substitution here was key, obviously. This 1 and 2, equations 1 and 2, to make this problem easy to solve, right? But to solve this problem, we need to know this and know this. And these are the things that they are given as assignments. Why A dagger, the commutator of A dagger is equal to 1? Because that's remember that what we need is to know what is A dagger, because A dagger is equal to 2 times n plus L. We don't know what is A dagger A. So that's why, sorry, we don't know what is A dagger. We know what is A dagger A. So this is a little bit confusing, but as you can see, all the calculations are here, and you just need to do them yourself, plus the additional work of knowing every detail on how we reach to this 3D energy of the harmonic oscillator. So now we're going to explore this. We're going to explore this further. For that, I'm going to
So, Prof, did you say like
Tell me.
A dagger and A is equal to N, and all of them they're equal to 2, is it 2M or is 2N?
2m plus L.
What is the value of M?
We're going to say now. It goes from 0, 1, 2, 3. We're going to see that now.
Oh, okay.
With an example. Here we have a table. If we go back to the lecture notes, if we go back here to the lecture notes, everything is nicely explained here. You go through the lecture notes as well. But there are some steps that they need to, like we have done. The last step is not here. How to reach to this point. Once you substitute X and P here, right? So, but then we're going to answer the question right here. So we're going to do it ourselves. So you can see later on this table there for your reference, but we're going to do it one by one, slowly, and taking our time to understand these things. So, no, I don't want to say this. All right, so we have solved the Schrodinger equation so far, and we have deduced the eigenvalues for the 3D harmonic oscillator, which depend on N and L, and this is equal to h bar omega 2m plus L plus 3/2. And now we're going to deduce what this is all about. So N, L, we're going to make our little table as we have here, and we're going to explain things. So we're going to have a level, which is going to be a wave function, actually, NL, which is going to be this one. And this wave function is going to be characterized by NL. We're going to have an occupancy given by the Pauli exclusion principle. Remember that these guys are fermions, and they must obey Pauli's exclusion principle that no two particles exist with the same quantum numbers, right? And then here we're going to put the energy of the particular orbit. So this is an orbit. This is the number N, L, the occupancy. So we're going to make our little table. And the purpose of this table is, remember, we have from the beginning, we have to solve this. And we have a harmonic oscillator, which goes to infinity, but this is a R here. And then we want to see what are the levels, excited levels in the harmonic oscillator, right? These guys here. So for that, let's begin by giving this guy the 0, 0 value. So that will be 0, 0. The occupancy will be 2 times 2L plus 1. 2, because there's a possibility to have the spin up and the spin down. So for the, as I said before, L can be equal to S, P, D, F, G. This is the nomenclature, but basically this is L equal to 0. This is 1, 2, 3, 4, 5, etc. Right? So we can do this. Occupancy of this level will be L is equal to 0, so it will be just 2. And the energy here will be, this will be 0, so will be this will be 0 also, L equals 0, and this is 0, this is 0, this will be 3/2 of h bar omega, right? So now we go to the next case, let's say a 0, 1, which in this case, 1 is P, right? L is equal to P, which is equal to, in this case, will be the 0, 1 or the 0P, let's call it the 0P. So we know when we see this nomenclature that this is 1 anyway. So this is 0 and this is 1. And now we have a 1L here. So this will be L plus 3/2 will be 5/2. So this will be 5/2 of h bar omega, right? And we have the energy here, this 5/2 of h bar omega. And the occupancy, as you can see now, L is equal to 1. So 2 times 1, 2 plus 1, 3 times 2, 6, right? Now we go and let's look at the 1s. This was actually the 0s. This 0 actually corresponds to s, right? So the 1s means that n is equal to 1 and L is equal to 0, right? This 0 here. So n is equal to 1. The occupancy, they will be the same as for this guy. The occupancy will be 2, but the energy will be let me see, is n is equal to 1 here. 2 plus 3/2, that will be 4/2 plus 3/2, 7/2, right? 7/2 of h bar omega. And then we have we can keep going and we can say, okay, let's look at the one or the 0d, which is 0 here, but now d is 2 here, right? So 2 plus 3/2 also is 7/2. But in the occupancy, this 0d, we have 2 times 2, 4, plus 1 times 2, 10, right? So basically, this is what is happening. What is happening is that we are making these fellows, we are making, in the first one, we have 2. In the next one, we have 6. The next one, we have 2. The next one, we have 10. Now let's go, let's keep working on this. Let's call this now let's say the 0s, 7/2. We can now go to the 1p. And then you have 1 here and 1 here. And basically you can keep going. And you know, we can P, F, G, H. You can keep going down here, but you see, in the next level we have 9/2 and 9/2. So that will be 1p and 0f. You know, here will be 0f, which will be 0 and 3. And this one will have 9/2 h bar omega, and there's also 9/2 of h bar omega. But what I want to say now is that we can put all these things here now, and knowing that this guy is the 0s. The next guy is going to be the 0p. The next guy is going to be the 1s. And the next guy is going to be the 0d. But now we see that these two guys are degenerate. So they were not written properly. They should have the same energy, right? Because they have both the same 7/2 h bar omega. So these two should be together, right? Because they are degenerate states. The degenerate states present the same energy, right? So and so on and so forth. Also, this 1p here and the 0f, these two guys will be the same, and the 0f will come together. And so let's write it down properly. So we have a Hamiltonian, which is the harmonic oscillator. Let me see now. And we have R here and VR. and we have a Hamiltonian, a potential, which is a harmonic oscillator, right? And then we have all these levels here. We have the zero P is here we go. We have this guy here, and we have this guy here. Let's just draw this four, although we can continue. And this is going to be, let me see, this is going to be the 0s. This is going to be the 0p. This will be the 0d and the 1s together, same energy. And the next one will be the 1p and the 0f with the same energy, right? So now these guys, in terms of occupancy, they will have to follow the Pauli principle, and they will have to go here, as I say, with two guys here. This guy will have with 1, 2, 3, 4, 5, 6. This one will come with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, plus these two. 1, 2, 4, 5, 6, 7, 8, 9, 10, plus the other two from this guy. And this guy will also come, the 0p's. The 0p's come with 2 times 1 plus 1, 3 times 6. 0p has with 6. 1, 2, 3, 4, 5, 6. But the 0f, the f is equal to 3. So the f is equal to 3. We have an occupancy of 2 times 3 plus 1, 7 times 2, 14, right? Plus another 14 here. 1, 2, 3, 4, and 10. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, right? And this is the way we are going to put all these guys in these levels. And for our purpose, the relevant part is how the nucleus look like. So this is the question we want to ask ourselves. And this is how the nucleus will look like. So this wasn't very tidy, I think. Let's make a new one. Let's make a new one. So how does it look like a nucleus which is vibrating, right? So again, I want to outline this picture here. We have a harmonic oscillator, and we have these guys and this guy. And these guys, as you can see, they are all separated. That's the 0s, right? And this is the 0p. They are all separated by h bar omega, because you remember this energy here is 3/2 of h bar omega. This guy has an energy of 5/2 of h bar omega. And this also, the next excited level will be another h bar omega difference. And this will correspond to the 0d and the 1s, which they have energy of 7/2 h bar omega. And so on and so forth, right? H bar omega. Basically, all this level will continue up there, and there will always be a difference of h bar omega. And this h bar omega is normally given by 41a to the 1/3 in MeV. So it depends on the nucleus itself. For oxygen 16, we'll have 41/16 to the 1/3, and that will be the energy here. For oxygen 16, for instance, the harmonic oscillator, the energy difference between one level and the other one will be 41 times 16 to the 1/3. That will be 103 MeV. 103 MeV. And now we see that for a nucleus which is vibrating, we will have structure, the ground state will be a 0 plus, the next state will be a 2 plus, and the next state will be degenerate, will be a 0 plus, 2 plus, 4 plus, and this will be a typical nucleus, which is, you know, say 62 nickel, has this structure, and many nuclei have this structure. But this is the ideal case, although this is not degenerate. Generally, these levels are close line with each other, and then they will decay by gamma rays. But this energy will be the same as this energy, right? In correspondence to the harmonic oscillator. So if this energy, a typical 1.2 MeV, this will be 2.4 MeV, right? Around that energy. So this will be a nucleus which is actually vibrating, right? Vibrations. So nuclear vibrations will look like that. And when we look at the spectrum, I want you to tell me how in our energy spectrum here, and the counts here, how this would look like. So these are the energy of the gammas, right? Energy of the gammas. So basically, it's clear that the energy spectrum of a vibrator, like nickel 62, we have a one peak here, which will be this guy, 2 plus to 0 plus at 1.2 MeV. But these energies are the same as this energy, right? So there will be also smaller peaks, but around the same energy, right? So basically, you will need to separate those energies because you will need very high resolution in your spectrum to distinguish these 4 peaks, which are coming almost together, right? Remember, there's a clear difference between a nucleus vibrating, and this is always a question that I want you to understand, and a nucleus which is rotating, which we have the similar energy spectrum, and energy in kV, right? And for a nucleus rotating, we remember we said at the beginning of this class, which was something equidistant, but in terms of gamma rays here, this guy is equidistant in terms of excitations, right? The vibrator has the same energies here. So this will be twice the energy of this one, right? But the transitions will be absolutely coming at the same energy. This will be 1.2 MeV, this will be 1.2 MeV, 1 MeV, but you know, around that energy, but they all come around the same energy. If the nucleus is vibrating, right? If the nucleus is rotating, then we have this E gamma will be the same. Actually, no, the spacing will be the same, but here the actual gamma rays will be the same, right? This will be different. E gammas, obviously, there are different energies. In this case, they will all come together, and you will need high resolution to distinguish, to separate them if they are actually a very good vibrator. These energies are exactly the same as this one, right? So we know how a nuclear vibrator will look like and how a nuclear rotor will look like. This is a rotor, and this is how it looks like. This is a vibration, and this is how it looks like. Now, something very important for this Hamiltonian, we have that V over R is equal to 1/2 of KR squared. So this implies that for a nucleus with the same R, the potential is the same, right? So this implies that nuclei, this is generally the case of this as obviously spherical symmetry. spherical symmetry. In our harmonic oscillator potential, we have a spherical symmetry, and that allows for a vibrating nucleus, which the nucleus is also spherical, right? So spherical nucleus. In this case, the nucleus in the rotor must be deformed, right? There's a big difference between spherical nuclei and vibrations and deformed nuclei and rotations. Okay, I think here I want to ask questions, guys. I've been talking a lot. My throat is hard. So,
how did we get A to be 160?
sorry, A to be 160.
Yeah, on H bar.
Oh, okay, because you know, this is the formula that we are using. Let me just share the screen with you quickly. Where you know? Am I sharing the screen now? No. Let me see.
Not yet.
Okay, here we go. Good, Lucy. That's a very good question. So when we this is the formula, and this formula is not so easy to deduce, but if you want, we can deduce this formula, but basically comes from here, 41A to the 1/3 MeV. So this is the difference between major shells, H bar omega, and a major shell, but I don't want to get into the shell model now, but this is basically it's going to be the essence of the shell model, but this is how I got 163 here. Okay, for the particular nucleus, for each nucleus, for oxygen 16, you just change D here by 16, right? And you will get 41 times 16 to the 1/3, right? And that is the 163. Oh, 103, sorry, 103. No, it's not 160, 103. Is that what you ask, Lucy? Is that what you asked?
Okay,
yeah. Okay. For each nucleus will be different. So 20 neon, you know, H bar omega will be equal to 41 times 20, in that case, to the 1/3. And that will be 111, right? 111, which will be the difference, the energy jumps in this harmonic oscillator, right? Each jump from one here to the next will be 111 MeV. So is that right? Let me see. 41 times 20. Actually, I think it's to the -1/3. That seems to. See, I think this formula is wrong. I think it must be a minus here because this is too big. I just realized that. Let me see. Let me see. Unified nuclear models. I have a nice book here. Yeah. It's called the practitioner shell model. Yeah, it's a to the -1/3. How this thing is determined. So it's a to the -1/3, not a to the 1/3. So this one was too many MeVs. So the oxygen 18, 6 or 16 will be. It's good you ask, you know, because as I say, memory is not a good partner. Times 16 to the minus 1/3, and that was 16 MeV. So basically, this for the oxygen 16, what is it? Am I here? H omega is equal to 16 MeV, and this is wrong. So for neon 20, it will be 20 to the minus 1/3 times 41, which is 15 MeV, not 100. It's important that we know more or less what these shells, 100 MeV will be very difficult for one particle to move from here to here, and that will be impossible to create any nuclei. So this mistake of minus by having a plus here will affect tremendously our world, So it's good always to have an estimation of what is the energy required to excite a particle from one shell to the next, to promote one particle to the next shell, to the next level. So 100 MeV is too much, and this was a mistake. So it's good that you ask these questions, guys, because then
Prof,
tell me.
why is the nickel has low energy compared to oxygen? 16.
The neon.
Yeah. I mean, a value for H bar W is small compared to like.
So we have 16 over 15, right?
No,
because
for
of oxygen versus 20. This one, no?
Oh, now I was checking the value for nickel, like this example.
Oh, for nickel. Yeah.
It's very small compared to oxygen. Why?
Right. So the tendency will go to this minus. It will decay. It will get smaller and smaller as you increase A, right?
I see.
Because let me see. Because as we have, this formula of the H bar omega is a very important formula because it tells us, and we'll learn more in the Nielsen model. But this formula, A to the minus 1/3 of MeV, or let's put it down like this. This A 1/3, right? MeV. So obviously, the bigger is A. As A increases, this will become smaller, right? And this implies that, for a nucleus with like oxygen 16, where in principle the H bar omega is equal, I like these questions because we can explore together. So this is 41 times 16 to the 1/3, to the minus 1/3. The minus 1/3. This is 16 MeV. And if we go to nickel, let's say nickel 62. Let's calculate it first. Nickel 62, we have 41 divided by 62 to the 1/3. We have 10 MeV, right? So this becomes smaller. 50, we say 62 nickel. So H bar omega is equal to 10 MeV, about 10 MeV. So as you can see, the jumps become smaller and smaller as you keep going. We can go to let's say lead-2-8. This jump will become smaller. 41 divided by 208 to the 1/3 will be 7, only 7 MeV. Let see if we can go there to the right. Yeah. 7 MeV. Right. So this decaying in energies basically implies that within the harmonic oscillator, the more particles you have, the easier it's going to be for one particle to get to the next level. The levels will get squeezed down in a way that you need basically more energy to promote a particle here in oxygen 16, to promote a particle from this level to the next level, because you need a big jump of energy with respect to a particle from here to here, which will be a relatively easier 7 MeV. No, almost here we need double the energy to jump this big energy gap. There's a big energy gap, right? And this energy gap will be bigger. And when we look at the excitations of oxygen 16 and lead-2-8, we can always compare what is the situation by looking at the NNDC. And let's see what happened in the NNDC. So in the NNDC, this is our database. We can always look what is happening in oxygen 16. And we'll see that our first excitation, let's go here, charge of the nuclides. And we can go, let me see to oxygen 16. Here we go. This guy here, I just click on them, and you can see the list of levels here. The first excitation is a 6 MeV, right? It's quite high. First excitation is at 6 MeV. It's a 3 minus a 6 MeV, also 6.1 MeV. But if we go to lead-2-8, the first excitation, it shouldn't be so. Here we go, lead-2-8 here. Even if both are, we will know they are magic numbers, the first excitation lead-2-8 is going to be much smaller, and it's going to 2.6 MeV, right? So more than double the energy in the case of the oxygen 16, 2.6 for, you can see here properly, 2.6 MeV or 2600 keV for the first excitation in lead-2-8, whereas for oxygen 16 we have a first excitation which is double the energy, more than double the energy of the one in lead-2-8. You see that? So as you can see, this energy gap is much bigger than in this case, and this is the prediction from the harmonic oscillator. Okay. Punto. Good. Who was that? Ganinshuti, who asked?
Yes, sir. Yeah, it is me.
Get it. I like questions. See, these questions are providing us, we solve a mistake. This interaction is very important because then we can always improve things. So we know that it's 41a to the minus 1/3 MeV. 100 was too much, 111 or whatever we were calculating was too much. And this actually comes from the square mean radius. There's a calculation that for the harmonic oscillator, which can be deduced, and to get this h bar omega equal to 41a to the minus 1/3. And then secondly, we also deduce that, as we increase the nucleus in size, then the energy gaps becomes smaller, right? And this is also an important point to understand that when we look at the NNDC, the energies are going to be smaller, lower excitations in lead-2-8 as we expect for oxygen 16, right? So, any more questions? Canichuti, you're winning points today, and also Luasi. And Fundo, what happened with your screen? Are you good?
Yeah, I think it was the network on my side, but
Okay.
now.
Okay. So on Friday, we're going to keep moving. We're going to keep moving, and on the next step, guys, is we have solved the energy. As we say before, we have solved the eigenvalues here. For the harmonic oscillator, we know that for the 3D harmonic oscillator, h bar omega, and then this is 2n plus L plus 3/2, right?
Can you
So
please share the screen, sir?
Yeah. We have solved the issue of the energies, which was quite important because there was through the second quantization, right? We have solved the problem very nicely, but the next step is to determine the wave functions. The beauty of the harmonic oscillator is that mathematically is very powerful, it's very tractable, and computationally is nicely to work with, as we're going to see in the next lecture, where we're going to deduce the wave functions, and then we're going to have the full picture. We're going to have the 0s. How does it look like? You know, we're going to have the wave functions and the energies, right? This was a 3/2 h omega, but we want to know what is this wave function here. What is this? This is our question mark for next lecture. What is this wave function here? 1s or 0p, you know, how this look like mathematically, right? And we're going to see that it's very easy to solve, and we're going to admire the power of the harmonic oscillator, of the Schrodinger equation, because it allows us not only to get the eigenvalues, but also the wave functions. And with the wave functions, we can just work in any code. We're going to learn also, we're going to have a PC prac where we're going to run calculations, share model calculations, where you are going to calculate the excitations of a nucleus. So far, we look at lead 2A, right? We see that the first state is 2.6 MeV, 0. We always call 0, but we know it's not. There's no 0 energy. It's a reference. It's a 3 minus. It's a 0 plus. So this is lead 2A. But what we're going to do is actually calculate these things. We know experimentally what is happening on the N and the C. But once we get the eigenfunctions, we can actually do proper calculations, and we're going to compare with these fellows. But this will be later on. So far, I just interested to know, for you to know how to solve the harmonic oscillator and see the beauty of solving the Schrodinger equation and compare with experiment what we see. Is this what we are expecting, as we saw for the rotor, and we saw for instance for the nickel 60 or nickel 62, which we haven't observed here, but I can show you quickly. CD, let's see, desktop 60. Okay, LS2 PDF. There's 62 NDC. Let's see, here we go. PDF. And we go here. And we look at the NDC always. We compare with the experimental data and we see what is happening. Look, first is always reference 0, but we know it's not 0. Here we go. Let's look at this. Let's close these things, otherwise we get lots of memory. And that's the last bit for today. I want you to be able to see how a nucleus, which probably is vibrating, looks like in real life. So we go to the here, this is nickel 62. So we just make our level scheme. And we write the first one is our ground state, which is 0, 62 nickel, but we know it's not 0 because this is actually the energy of the binding energy, right? Which is equal to the mass of the 62 nickel, you know, minus the masses of the proton. You know the question. But this is equal to minus the energy. So it has a negative energy here, which corresponds to the binding energy of nickel 62. Right? There's no such thing as zero energy in quantum mechanics. So the next state happens at 1 point. You can see here at 1.173 is a 2+ state. Here you have the total angular momentum J and the parity 2+. So then we move here 1.173, 1.173, and then we know this is a 2+. Then let's look like here we go. The next one, as I say, is a 0.24, 2.2049. Let's put them here. 2049. So it is a little bit higher there. 2049. Then this other guy is oops. Sorry, I just touched the wrong. A lot of information on nickel 62, as you can see. Next one is 2049. Next one 2302. 2302. And this other one is 2337. 2337. 2337. This is a 4, 2, and 0. It's a 0+, the 2+, and this is a 4+. Okay, so as you can see, this energy 1173 is similar to these energies that are going to decay to this fellow, but this guy is 2049 minus 1173 is going to equal to 876, which is now questioning whether this is a vibration already. But let's look at the other ones. 2302 minus 1173. This is 1129, which gets quite close, right? And this energy here is 2337 minus 1173, which is equal to 1164. So 1164, which is quite close to this value here, right? So this is how a nucleus which is vibrating may look like, but there's a big question mark here. So this is not the same as this one. This is not exactly the same as this one. This is quite okay, right? And this is what we investigate. You know, are these guys actually vibrational? For this to be vibrational, this state must be spherical, perfectly spherical. And this is determined by the quadruple moment of this state in particular. This is the quadruple moment. And this is an experimental value that we can measure, we can determine. And this is what our students are doing with the GAMCA array. They have data to determine whether this is this particular nucleus has a spherical shape, which is what, as I mentioned before, what the harmonic oscillator predicts, right? If this has a spherical shape, then probably the nucleus is vibrating, it's oscillating, and that's why the measurement of this value here is very important. So this is for this we have used all the detectors in the GAMCA. There were like 13 detectors at that time, and we ran a reaction. You know, this is another story for you to tell you another time. But we are trying to deduce basically what is this shape of the nucleus, which if it's spherical, this must be equal to 0, right? So this is a big question mark that we don't know right now whether we are 0 or not. This was one of the first experiments using the Gamka array. And you know by now what is Gamka, right? It's a beautiful array, which is now the Temba Labs. We ran this experiment in November 2019, just before the COVID-19. So we are finishing this analysis. The students are submitting their thesis now, and we have the possibility to study this kind of physics. You know, whether the nucleus is spherical or not, whether the nucleus is vibrating or is rotating or is doing something else, is to be determined. So this is why we investigate nuclear physics, and this is how, you know, this tiny thing, very, very tiny thing of a few Fermi apart, that we can determine the shape of that tiny thing is actually quite remarkable, right? A positive shape will look like a rugby ball. A negative shape will look like a lentil, and a spherical shape will be like that, right? So this is that this nucleus, a few Fermi apart, right? How much is the radius, guys, of the nickel 62? Assuming a spherical shape, the radius of the nickel 62 is 1.2, right? A to the 1/3 Fermi, which is equal to 62 times exponential 1 divided by 3.
Like 5.
Times 1.2. You know, imagine almost 5, right? 4.8, 5 Fermi, about 5 Fermi. 5 Fermi, you see, 5 Fermi is 0.0000000. You know, that's how many 12 to make centimeters, right? It's 10 to the minus 15 meters, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 meters, or, you know, we can move on centimeters, right? So this tiny thing that we can actually determine the quadrupole moment, the shape of a nuclear level, is, to me, mind-blowing, you know. That we can deduce an excitation there. We can excite the nucleus and determine what kind of shape, whether this one, a lentil, a rugby ball, or spherical shape, or something else, you know. Remains to me a miracle that we can actually, not a miracle because we can do that, but it's just quite impressive. Don't you think so? So I'm going to stop sharing now. And that's it for today.